We introduced Biot-Savart law and we derived it. So now, once we know the current distribution, we can perform a closed loop integration to arrive directly at B vector. B is our magnetic flux density. So that is a very powerful tool. As compared to Ampere's circular law, we can now try to find out the resulting B for arbitrary geometry. Okay, we don't rely on particular symmetries. So now let's take a look at one example. This is again a fictitious example. We have a wire of finite length of 2L. And we're now trying to look for the B field at an observation point which is bisecting the wire. So now we have one L and another L. So the observation point is here, bisecting the wire, and the distance is non-capitalized R. Right? We want to invoke Biot-Savart's law. So to use it, well, of course we already know the current conducted by the wire, which is I. So all we have to know is when we perform the closed loop integration, we have to have a clearly defined differential length. And for each differential length, that piece of segment has a corresponding distance, capitalized R. And for each distance, we have to have a defined unit vector in terms of the distance vector. Okay? So all we have to do is find out the proper expression for differential length, the unit vector, and the distance for each piece of the current segment. So let's come back to the figure. Assume we're now trying to find the contribution of B field for this differential segment. So the differential segment has a length of dz prime. In this case, we want to use cylindrical coordinate. Why? Because a wire is best represented by cylindrical coordinate. Alright? Of course, the wire is not having its own radius. Right? So the wire is positioned in the z direction, and therefore this differential segment is in the z direction, and each one is having a magnitude of dz prime. Again, I'm using the prime system to denote the source. Right? Therefore, for this piece of differential segment, its distance to my observation point is labeled capitalized R distance vector. And that distance vector can be represented by the z location, the vector z, right? And the distance from my observation point to the bisecting point I denote as the origin of the cylindrical coordinate, right? So basically, this distance vector is the non-capitalized R vector minus the z vector, okay? So AR, R minus AZ, Z prime. Again, Z prime denotes the source coordinate. Well, this current form is having the non-capitalized R and Z prime. But eventually, in this equation, I'm looking for something expressed in terms of the distance, the capitalized R, the magnitude of the distance vector. So somehow, I want to express everything using capitalized R. So this R, now you draw this triangle from trigonometry. We know that the non-capitalized R is the capitalized R times sine theta. Theta is the angle here. Okay? And Z prime is R cosine theta. Now we can express the unit vector easily by normalizing everything, just divide by R, right? This R vector divided by its own magnitude becomes the unit vector. So the unit vector is now in the R direction, the radial direction with a magnitude of sine theta, and minus the Z unit vector cosine theta. Right? So now we know this. We know this. Do we know dl prime, the differential segment, differential length? Of course we do. It's in the Z direction and with a magnitude of dz prime. Right? So now in the numerator, we can perform the cross, right? The cross product. So dl prime cross my unit distance vector. I can just write it out. Well, in this case, we're lucky. Why? Ideally, my unit vector has two components, right? Two directions. But eventually, my differential length is in the z direction. So z cross z becomes 0, right? When you're making cross product, you have to have non-parallel components. So we're lucky we only have one resulting term. And this is a test to you. Z cross R. Z cross R, right? Z is now here, pointing upwards. Z cross R. R is here. Z cross R is, your thumb is pointing into the board. Meaning, the resulting direction is in the phi direction. So therefore, we have A phi, and the magnitude is sine theta dz prime. Okay? Therefore, the integration to use the Biot-Savart law, we only have to perform, well, in this case, we don't have a closed loop, but this equation works well, okay? We only have to limit the lower bound to negative L and upper bound to L to truthfully reveal the geometry, right? Totally, I mean, this segment has a length of 2L, right? But think about it. When we look at here, we are trying to integrate over Z, the locations of each differential segment. And if you look here, it's R squared is, well, seems like independent of Z. And sine theta, in this case, initially, naively, seems independent of Z prime. But that's not true, because whenever you change this theta value or this Z value, everything changes, right? If you try to integrate or try to find the contribution of this segment, theta changes, Z prime changes, the Z location changes, and R changes, right? So actually, these are all Z dependent. So we have to find a way to properly formulate everything in a single parameter, right? So the easiest one is to convert everything using trigonometry to be theta dependent. How can we do that? Well, look at the geometry. This distance magnitude is R cosecant theta, and Z prime is R cotangent theta. So now we find a way to convert the distance magnitude using theta, and also Z prime using theta. And from this equation, we can find the relation between dz prime and d theta. So we can convert everything using one symbol, theta. So theta is now becoming our variable. Okay? So after the conversion, I have a purely theta dependent integrand. Okay? This is purely math. You have the notes, so you have to spend time on your own. I'm showing you the results, but there is one caveat. You have to be careful, right? The way I label theta 1 and theta 2 is extremely important. Why? To make everything consistent, when I'm trying to integrate the lower bound, I have defined theta 1 as the angle between z and my distance vector. Okay? Once I have defined theta in that way, when I change my theta value over to the top, when I reach positive L, the corresponding theta has to be defined in the same way. It's the angle of z and your distance vector. So this is actually my theta 2. It's not this one. Okay? You have to remain uniform. Your definition has to conform everywhere. So for the lower bound, the angle is z, between z and distance vector. So your upper bound has to be also the angle between z and the distance vector. Right? So a lot of times students are making mistakes. Well, eventually the result is cosine theta 1 minus cosine theta 2. But if you define theta 2 incorrectly, then your result will be wrong. Okay? So what I'm trying to say is the value of cosine theta 2 is actually negative, even though this is cosine theta 2, right? You think, well, you have an angle, and if you take a cosine using this triangle, it's L divided by this piece. But to be correct, your cosine theta 2 has to be a negative value. If you take it positive, cosine theta 1 minus cosine theta 2, if you take it positive, you have 0. So why is cosine theta 2 negative? Well, if you still remember, cosine, positive, negative, negative, positive. Cosine is positive in the first and fourth quadrants, and negative in the second and third quadrants. Look at the geometry here. When I define theta 2 as this angle between z and r vectors, this angle is evidently greater than 90 degrees, right? Meaning theta 2 is actually pushing into the second quadrant. So if you're into the second quadrant, you have to know cosine must be negative, right? So you have a negative value. Well, another way to think about it is cosine theta 2 is negative cosine theta 2 prime, right? This theta 2 prime is positive, but because they're complementary, they add up to pi. So theta 2 must be a negative value. So this is a care that you have to pay attention to, right? In the end, if you do everything correctly, you will arrive at a beautiful result, right? For this wire with a finite length, the resulting B field is in the phi direction and with a magnitude of this expression. Now, if you still remember, we used Ampere's circuital law to find the B field of an infinitely long current conducting wire. Can you somehow just make some assumption so that the two results will merge together? How can we arrive at the result for an infinitely long wire? Well, you just assume L is going to infinity, right? When L is going to infinity, or L is much, much larger than the non-capitalized R, this term is gone, right? And then you have mu 0 I divided by 2 pi R. If you compare the result we got using Ampere's circuital law, they are identical, okay? So every time, whenever you perform some calculation, at the end, don't just close the book or just turn in your homework or examination. Do some self-consistency check, right? You have to, your answer needs to be tested, all right? So in this case, make L very big. You can ignore this one. Therefore, you arrive at your familiar answer for an infinitely long current conducting wire. Okay, next example. Well, if you still remember, Biot-Savart law has two formulations. One is using unit vector, another one is not. They are identical, but there are two different forms. So now I'm using another example. Okay, I have a closed loop conducting wire. So the circular loop is having current value of I, and the radius is B. Okay, it's B. Currently, I'm trying to find the resulting B field for an observation point of 0, 0, Z, which means I'm on the geometrical center, but now I have a height of Z. So again, this is only to illustrate the power of Biot-Savart law. But ideally, this observation point could be anywhere, okay, to make it more generalized. But at the moment, we are asked to find the B field at this particular point. Why? Because the textbook is trying to be nice. Think about it. When the observation point is on 0, 0 and having a Z value, it implies we have some beautiful symmetry. Okay? So at this moment, can you guess which direction is your resulting B field in? You are exactly at the center, the top of the center of this circular loop. Would you expect to have any radial component or phi component, or just simply Z component? Think about it. If you're trying to use Ampere's circuital law to solve this problem, then it relies on your deep understanding to the system. But if you use Biot-Savart's law, ideally you just do everything, all the calculations brutally, and you will get the answer right. You don't really need to have physical insights or deep understandings. But that's not what I want to train you. I still want to train you in a way, before you perceive any problem, you can predict or foresee the result. Okay? So each piece of current segment is producing what your current direction, in this case, is going in the direction of your thumb. So your B field is following the direction of your four fingers, right? For example, this segment, right? So if I'm standing here, I should somehow feel the B only in the Z direction, because each segment would cancel out the other directions other than Z. Okay? So if you have this anticipation in your derivations, even using Biot-Savart law, you would pay attention to some vanishing components. Okay? Alright, so in this case, for each differential segment, easy to describe. dl prime is b times d phi prime. Right? Now we have a radius, so basically each differential segment is actually an arc. So b d phi prime defines the arc length, but in the direction of phi. My distance vector is this r, capitalized R vector, is therefore z vector minus my b vector. Okay? Therefore, the magnitude, the distance of each differential segment to my observation point is therefore the square root of z squared plus b squared. Okay? So I know this r. And I already know this dl prime, I know this r. I have everything. Right, so I can just do the cross product of dl prime to r vector. I write everything out. So this is the point where you have to decide again, if you understand the problem correctly and deeply, you can save half of the time as compared to your fellow students, fellow classmates. In the end, dl prime cross r vector is now arriving at two components. One in the z direction, another one in the r direction. Just like I said, do you want to put both components into the closed loop integration? Well, of course, if you don't have any physical insights, if you don't understand this problem, go ahead and just do it. Put the two components into the closed loop integration. It's fine. If you do the math right, it does not affect your result. But up front, if we only anticipate to have non-zero z component, which means the r component can be dropped at this moment. So think about it. As I mentioned, we don't expect to have any components other than z, which means at this point, this AR component must vanish. And therefore, you don't even need to bother to calculate it. But you have to convince yourselves. Why can't we just ignore that component? Well, it is because in the current case, we're trying to observe the B field at a beautiful phi symmetric point. We are exactly at the top of the center. So therefore, all the segments will give you R component and Z component, but eventually this one and that one will cancel out in terms of the R component. Okay? So in this case, it's due to the symmetry of my observation point being exactly at the top of the center of the circular loop. Therefore, you only have remaining Z component in terms of B. But if I change my problem to, well, my observation point is really arbitrary, you have to include this term into calculation. Alright? Okay, so due to symmetry, we don't have any R component, we only have Z component, as we expected. Right? Which is nice. So then you just perform the integration. And in this case, we're lucky because b is just constant, z is nothing dependent on the source coordinate. So you just multiply by 2 pi. Okay? So this is the second example. But what I'm trying to tell you is, although Biot-Savart law is extremely powerful, but there are still moments that rely on your understanding prior to the mathematical procedures, and you can save time. Okay? In this case, you are dropping one contribution out, so in your integration, you only work for this one, you save 50% of the time.